Dagger Team 1, are you seeing this? There's some kind of disturbance here.
Davis, what is that? What are you seeing?
What the hell?
Everything in this world has a form. The form can be solid, liquid, or gas. But there is a form that you may not be familiar with.
Solid, liquid, gas. Lava can turn into rock, ice can turn into water, metals can melt. These are natural states, but there are unnatural states. Bose-Einstein condensate. A state of matter that was predicted by Nath Bose and Einstein.
Well, what is mentioned in this film is not fiction. The Bose-Einstein condensate is the fifth form of matter after solids, liquids, gases, and plasmas. It is called Bose-Einstein because this form was invented by two people, Nath Bose and Einstein. Unfortunately, you can't see this form of matter every day because it is a quantum phenomenon and is only created in very, very cold conditions.
Einstein predicted that this state of matter would exist, but he thought it was at such a ridiculously low temperature that you would never be able to actually observe it.
It's so cold it will kill you instantly on contact, and it can do everything that we've been seeing.
Interestingly, this form has superfluid properties, meaning that it's very smooth so that it can penetrate anything without hindrance.
Did you see that? The bullets went right through it.
Did he miss?
McFadden doesn't miss.
The fluid becomes a superfluid, which means if you pass something through it, like your fist, right, there is no resistance to your hand moving through that volume.
If you look down here, you will actually see the cold cloud right there in the center of the vacuum.
So what exactly does this material look like? Why was it formed, and is it dangerous? So much so that NASA had to lock it up in space.
Gravity had a big effect on these systems, and it would be interesting to do these types of things in space, even though it was totally crazy to even think about.
Therefore, guys, prepare the intellect and prepare the faith, because we will enter the study that can make you crazy. Let's first discuss a glimpse of the Spectral movie. The film airs on Netflix, and it's quite interesting because it combines war movies with horror movies.
What the hell?
But the horror is not ordinary horror. The horror is scientific horror.
The agency thinks this is some kind of cloaking technology.
So this movie tells the story of the civil war in Moldova, and America is involved in this war. Once some of his troops died mysteriously, and from one of his eyeglass recordings there was an apparition.
In the last few weeks, we've been finding bodies around the city that were killed in the same way. Insurgent soldiers wearing active camouflage.
In this country, something that advanced.
At first they thought it was some kind of camouflage technology, but Mark Klein, the main character in the film who is also a scientist, thought it was something else.
I don't know what I'm thinking yet, but there is an explanation.
So he had to go into the field to see it firsthand. But what happened? His army was slaughtered by these creatures, and it turns out that they are not one or two, but many. Anyone who was touched by this creature instantly froze to death, as if this creature was created from something very, very cold. Locals thought they were ghosts of war victims.
Lost souls. Souls of the dead.
Unfortunately, these ghosts multiplied and attacked the entire city, so the situation became even more chaotic. But luckily, Mark Klein found a clue that this creature is not a human, not a ghost, but someone has created it in the lab.
I know what they are.
Someone made it.
Man-made how?
Bose-Einstein condensate. A state of matter that was predicted by Nath Bose and Einstein. Can pass through walls. It's so cold it will kill you instantly on contact, and it can do everything that we've been seeing.
With that knowledge, Mark Klein finally knew how to paralyze this material.
If my math is right, it should break down condensate.
Yeah, then please watch the movie yourself on Netflix. Now let's discuss the science side. In school, maybe you have learned that there are three forms of substances: solid, liquid, and gas. And all substances can change between these three forms. For example, water. Water at room temperature is liquid, but when you put it in the freezer, it turns solid, namely ice, and when heated to a boil, it turns into a gas. And this also applies to other substances.
Solid, liquid, gas. Lava can turn into rock, ice can turn into water, metals can melt.
Of course, each substance is different, at what temperature it melts, at what temperature it solidifies. But you get the point that the form of the substance depends on its temperature. The question is, what is temperature? That temperature is essentially the kinetic energy of an atom, or in short, how fast its atoms move in a substance. And that's what actually makes the form of a substance changeable. In a solid form such as ice, the atoms do not move much, aka rigid. But when you take the ice out of the refrigerator, the atoms absorb the energy from the surroundings, so they move faster and release their stiff bonds. That's where the ice melts. When water is heated again, the atoms absorb even more energy, so they move even faster than before until they finally break free from the bonds of water and fly into the air as a gas. And this actually doesn't stop there, guys. If you heat the gas again, the gas will change into plasma. Plasma is an electrically charged gas. Why is it electrically charged? Because once these atoms gain even greater energy, they release their electrons so that the positive and negative ions separate, creating an electric voltage. That's what happens to plasma balls and lightning. So up to this point, you should understand that the higher the temperature, the faster the atoms move, and the matter tends to scatter. But the lower the temperature, the slower the atoms move, and the matter tends to condense. But you have to note, even though the ice is solid, it doesn't mean that the atoms don't move at all. They can still move even if they are minimal, that is, by vibration. So the question is, what if the atoms don't move at all? What happened? The first thing you should know, if the atom is really stationary, then that is the coldest temperature. As we have already discussed, temperature is essentially the motion of the atom. The slower the atom, the colder the temperature. So when the atoms don't move at all, then that's the coldest cold. He called the point of absolute zero. And this absolute 0 point is not 0 degrees Celsius, but 0 degrees Kelvin, or the equivalent of minus 273.15 degrees Celsius. That is the lowest limit of the temperature. Nothing is colder than that. What's interesting, guys, no matter how hard we cool something, it will never reach 0 degrees Kelvin.
Has anyone ever got to zero?
No, you can't do it.
Why not?
You can never get there.
Why is that?
Because every time you...
If discussed at length, this has to do with the laws of thermodynamics and quantum theory. But in essence, the laws of nature prohibit atoms from being completely silent.
Because there's a quantum vibration that goes on, no matter how much heat you've taken out.
Now all scientists can do is just get close to the 0 point, not really zero. For example, 1 per 1 billion degrees Kelvin. That's what scientists can achieve the most. And to reach that temperature is very, very difficult. Special techniques are needed. But the most interesting part is that the closer to the absolute 0 point, the form is no longer solid, not liquid, not gas, but something else. This is what Nath Bose and Einstein predicted in 1924. So in 1924, Satyendra Nath Bose, an Indian scientist, sent a letter to Einstein, whose contents surprised Einstein. In his letter, Bose claimed that he could solve Einstein's problems in quantum theory. For those of you who don't know, quantum theory is a theory that studies the properties and behavior of particles and atoms, which is very strange, contrary to the existing laws of physics. Particles such as electrons, protons, and neutrons are real because they can be measured experimentally. But uniquely, their existence cannot be predicted mathematically. So it is said that the particle has the property of dualism, as a particle as well as a wave. In short, the particles seem to have their own hand when they will appear, where they will appear, and under what circumstances they will appear. So in quantum theory, the atom cannot be described like this, but like this. This bright part shows the particle is around it, but it is not known for sure which side it is. Well, Nath Bose in his letter said that light particles, or so-called photons, are not even distinguishable from each other. When Einstein read his letter, he was immediately impressed, even more enthusiastic than Bose himself. So Einstein then developed his theory of Bose and eventually led him to discover the fifth form of matter, which was later called the Bose-Einstein condensate. To understand what a Bose-Einstein condensate is, take a look at the following animation. At normal temperatures, the atoms in a gas will behave normally, each moving according to its energy level. Well, but as the temperature starts to drop, the wave properties of these atoms begin to become visible. The colder the temperature, the slower the atoms, and the greater their wavelength. And over time, these waves are stacked on top of each other, until in the end they all fell at the lowest level of energy and they merged into one as if they were one big atom. That's the Bose-Einstein condensate.
You just keep getting this colder and colder and colder, and the wavelengths of each of these particles gets longer and longer. And you reach a point where all the wavelengths overlap each other for every single particle. And they become one.
Well, but guys, what Einstein expressed in his paper is only theoretical. Einstein only predicted that this form of matter should exist and would be different from the form of matter as we know it. The problem is, in order to prove it, atoms have to be cooled to near absolute zero, which is not an easy thing because we're talking hundreds of degrees under the cold ice, where the atoms are literally almost stationary. But as technology evolves, scientists have finally figured out how to do it, using lasers. Maybe all this time you know that lasers are hot and can even cut steel. But in this case, the laser is actually used to cool the atoms. How? So the scientists set the frequency of the laser so that when the atoms are fired by this laser, the atoms will slow down because they are pushed by the light particles from the opposite direction. This is the same as stopping a moving billiard ball by hitting it from the opposite direction.
Here, we cool atoms down with lasers, and they get a recoil from it. Just if you hit a billiard ball with another billiard ball.
In this way, scientists can also lower the temperature by a few millikelvins.
If you look down here, you will actually see the cold cloud right there in the center of the vacuum.
But guys, that's not enough. Scientists had to proceed using a technique called evaporative cooling. Simply put, it's like blowing a cup of hot coffee. The difference is that the cup referred to here is a magnetic field which isolates the atoms. Then a kind of radiation is blown on it so that the hotter atoms will come out and leave the cold atoms. In these two ways, scientists were finally able to cool the atoms until the temperature that was digested for the Bose-Einstein condensate was formed.
Wait a minute. Okay, so
Yes,
that's the condensate?
That's the condensate.
But look at the temperature.
Yeah, it's very cold.
177 billionths of a degree. 177 billionths of a degree Kelvin.
This is the coldest spot in the universe.
Unfortunately, guys, this material form cannot last long. Scientists have so far only been able to maintain this form for between 15 and 20 seconds, a very short time. Why is that? Because atoms don't like cold by nature.
It is incredibly challenging making something ultra cold because there is nothing in the natural world that wants to be ultra cold. Something like this is so rare, so unnatural, so unlikely.
But there are unnatural states. Bose-Einstein condensate.
So unlike in a spectral movie, where the ghosts that are said to be created from this form can wander out and can even endanger humans. In fact, originally this form of matter was very vulnerable, so it had to be constantly confined in a magnetic field. That's why NASA is trying to do it in space. Why? Because one of the obstacles scientists created this form of the sun is gravity. The slightest contact with the outside world, the atoms will immediately absorb its energy, and this form will be destroyed instantly. By doing it in space, gravity is no longer an obstacle, so that this form of matter can float in the air and can last longer.
Gravity had a big effect on these systems, and it would be interesting to do these types of things in space. We think we can get to a new regime of even colder temperatures for even longer amounts of time.
Why then did scientists study it? Because there is one interesting character from this form, that is, superfluids. Of course, you are aware that something that moves will definitely experience resistance or friction, even if it is with air. Well, a superfluid is a condition in which a gas or liquid has no viscosity at all. so something can move in it without feeling any resistance at all.
The fluid becomes a superfluid, which means if you pass something through it, like your fist,
Right.
there is no resistance to your hand moving through that volume.
Well, but actually, guys, this superfluid property can still be produced without having to be as cold as Bose-Einstein condensate. This is an example of a superfluid of liquid helium cooled to about 2 degrees Kelvin. Notice that this container has no pores at all, but you can see as if the water is dripping down. What is subtle, the water drips down not because there is a hole underneath, but because this liquid climbs upwards through the side.
Below the lambda point, the superfluid component of liquid helium creeps up along the walls of its container in an extremely thin film. The film rises along the inside wall and comes down along the outside, collecting in drops at the bottom.
This means that this superfluid can even pass through the gravitational resistance once it moves. The bottom line is why scientists study these phenomena like the Bose-Einstein condensate, because many miracles happen in the quantum world that we can't witness in normal life.
This is really what we're made of. We're made of weird stuff like this.
This is the essence of the weirdness, of the spookiness in the quantum world.
This means that life is more mysterious than you think.